non-negative, then its first moment is always there, and it is number in 0 and to plus infinity included. So here, try to make a distinction between the, the statement that the first moment does not exist, or the mean does not exist, and being equal to plus infinity. So the mean can be finite, it can be plus infinity, so this is like sort of a case on its own, or it can be undefined, as we will see. But for non-negative random variables, it is always defined. It's always a finite real number, or it can be plus infinity. And how do we compute the first moment? So by definition, if your random variable is discrete, then you use this summation. So you take the possible values of the random variable and you weight each guy by its probability, which is the PMF. Okay. Now, if your random variable is absolutely continuous, then what you do is that you take the value of x and you multiply by the PDF. Note that the integration is from 0 to infinity, because again, till now we are talking about non-negative random variables. The first moment, of course, again, can be plus infinity. This is an interesting case in some applications. Okay, so what if your random variable is a general random variable? Okay, so it's basically, it can be positive or negative, like a Gaussian random variable. Okay, and there are so many useful random variables that can take positive and negative values. So the idea here, and again, this idea is not like sort of, it is based on how Lebesgue integrals are defined. So it has like sort of a solid mathematical foundation. It's the way that actually things are done in measure theory and Lebesgue integration. So it's not something that is far-fetched or like some arbitrary choice. So if your random variable can take both positive and negative values, you need to like sort of decompose it into two random variables. One of them basically, or both of them are actually non-negative. Okay, so we define this x plus. Okay, it is basically the maximum of x and 0. Okay, so basically x plus is a random variable. If random variable x is positive, then x plus is equal to x. And if x is negative, then basically x plus is 0. Okay, so when you take this function max x and 0, it means that again, if x is non-negative, you simply take it as is. But if it becomes negative, then x plus will be 0. So x plus is a non-negative. Is a sort of a non-negative transformation applied to x. Okay. Now x negative will be defined as such. It's minus the minimum of x and 0. Now what happens if x is positive? Now if x is positive, then the minimum of a positive number and 0 is 0, and minus 0 is 0. So basically x negative, if x is positive, now x negative will be equal to 0. What if x is negative? Let's say that x is minus 5, one of the possible values of x is minus 5, then the minimum of minus 5 and 0 is minus 5, and then there is a minus sign that is outside here. Okay, so it will become 5, right? It will become 5. Okay, so basically these two random variables, x plus and x minus, you can think of our random variable as decomposed into two new random variables, and I will comment a bit on this later. So what we are doing here is exactly that we are sort of applying a function to a random variable. Okay, so we have a complete chapter on functions of random variables, and if we want to do things rigorously, you need to ask yourself, is a function of a random variable itself a random variable? Okay, so again, if you remember that random variables are basically functions defined on big omega, and they are not any arbitrary functions, they are f measurable, meaning that basically the pre-image of any partial set should be part of your sigma algebra. So now if you apply a function, to the random variable, so it's like function decomposition. So there is a function x from omega to r, and then x plus is another function from x from r to r, right? So you are basically doing this, applying this function to the random variable. So is this overall thing f measurable? Okay, so you know, because we have so many things to do, we will not basically like obsess, you know, we will not like spend time on this issue. In fact, the functions of random variables in this course, you know, whenever you encounter a function that depends on one or more random variables, we will automatically take it to be a random variable. So it happens that all things that we use in practice, you know, basically satisfy this property that, you know, that again, we have functions, you apply them to random variables, you get what? You get random variables, okay? And you don't need to check this or anything. So we'll take this for granted, but again, there is a subtlety here when I say that, you know, this thing, so x, but now I'm talking about the max of x and 0. This is not x. This is a function applied to x. Yes, you can show rigorously that this is indeed a random variable. If x is a random variable, then max x comma 0 is indeed a random variable. Okay, but again, you know, let's basically go beyond this. X minus is the same story. Those are, you know, again, random variables proper. Okay, to give you like a feeling of what x plus is and what it, so assume that x is a discrete random variable and it takes those values with certain probabilities that sum to 1. So x can be minus 4. So x here is an example of a random variable basically that has a positive and negative values. So what will be x plus? So x plus will only take 3 values, you know. So when x is positive, x plus will also take the positive values with the same probabilities. Okay, so this is the probability that x is equal to 1, and this is the probability that x is equal to 2. But if x gets negative, okay, then it is set to 0. Okay, so x plus will be equal to 0, and this happens if x is 0, or if x is minus 3, or if x is minus 4. Okay, so this is our new random variable, which is x plus, and as you can see, its values are non-negative. X minus, now x minus, if x becomes positive, then x minus is 0, and so basically x minus is 0 if x is 0, or if x is 1, or if x is equal to 2. Now, if x is equal to minus 3, x minus becomes a 3, and if x is equal to minus 4, what is the minimum of minus 4 and 0? It is minus 4, and minus 4 is 4. Okay, so this is an example of these two guys here. Again, I didn't like show the details, but they are guaranteed to be correct random variables, and they are non-negative. And because they are non-negative, we can sort of compute the first moment by, you know, of each one of them. So each one of them will not be problematic in terms of computing the first moment. Okay, so we can go and compute the first moment of x plus and the first moment of x minus. Okay, using the definitions. Okay, which are basically formulas that look like this. Okay, so before we proceed, let's make sure that we understand basically how x plus and x minus are related. X itself is x plus minus x minus. Okay, x itself, if you want to write x in terms of x plus and x minus, x is x plus minus x minus, and you can verify this. Now, if x is 0, x plus will be 0 and x minus will be 0, right? So the three guys will be, you know, the three guys can be 0 at the same time. And x is 0 if and only if x plus is 0 and at the same time x minus is equal to 0. Now, if x plus is a positive, automatically x minus will be 0, okay, and this will be the positive value of x. Now, if x minus is positive, then automatically x plus will be equal to 0, and minus x minus will be the value of x. Right? Remember, x minus is always non-negative. Okay, again, if x is equal to minus 5, x plus is equal to 0, and x minus is equal to 5. So you can get back this minus 5 by doing x plus minus x minus. Okay, so this is x and how it's related to x plus and x minus. Now, if you just add x plus and x minus, you can verify that what you get is the absolute value of x. Okay, so again, here we decompose x into those two interesting random variables, x plus and x minus, and x plus minus x minus will give you x. If you add them, each one of them is non-negative, and if you add them, you get the absolute value of x. From the point of view of the first moment, you can compute using the formulas the first moment of each one of those guys, x plus and x minus, and we have 4 possibilities. What are they? You compute this expected value of x plus using the formula, okay? So if x plus is a discrete random variable, you simply take each possible value of x plus, multiplied by the respective probability, and then do a summation. Now, if this summation is a finite number, and if you repeat the same to x minus and you also get a finite number, okay, so this is the first possibility, then in that case, the expected value of x is a finite number, and it is defined, so you can take this as a matter of definition. It is defined the first moment of a general random variable. The first moment of a general random variable will be basically the first moment of the non-negative random variable x plus minus the first moment of the non-negative random variable x minus. Okay, so you basically subtract this from that, and this will be the expected value of x. Now, if you sum the expectations, you get the expected value of the absolute value of x. So this is the absolute first moment. And of course, summing two finite numbers give you a finite result. Okay, so this is like sort of the sweet case. So here again, expectation of x will be finite, expectation of the absolute value of x will be finite, and everything is defined, no problem whatsoever. But when you compute those guys, you may get another possibility, which is that this guy explodes to plus infinity, while this guy remains finite. Okay, so in that case, what will be the expected value of x? So again, we'll take it like you take this minus it. What is infinity minus a finite number? It is infinity. Okay, so infinity minus a finite number. So this infinity minus something that is finite is equal to infinity. So in that case, the expected value of x will be infinity plus infinity. And the expected value of absolute value of x is basically you sum these two guys, and again, infinity plus a finite number will also be plus infinity. So in this case, basically both guys are equal to plus infinity. And again, in this course, we will not say that the first moment is not defined or something like this. No, it is equal to plus infinity. It's a case on its own. You may have this case switched. So in you compute the expected value of x plus, you get something that is finite. But when you compute this guy, you get something that is plus infinity. Again, remember, x plus and x minus, each one on their own is a non-negative random variable. So when you compute its first moment, you either get something that is finite or plus infinity. So in this case, maybe this guy yields a finite result, and this other guy yields plus infinity. Then in that case, you have a finite number minus infinity. This will be minus infinity. And if you sum infinity plus a finite number, you will get infinity. So in this case here, expected value of x will be minus infinity. Again, something that is legitimate. And the expected value of absolute of x will be plus infinity. Okay, so this is the third case. Now the fourth case is that both guys are infinity. Both guys are infinite. Okay, so in that case, the first moment does not exist, because now, what is the rule for basically getting the first moment of a general random variable? You subtract basically the first moment of x minus from the first moment of x plus. Now infinity minus infinity is not defined. Okay, so in this particular case, we will say that the expected value of x, it does not exist, because what is infinity minus infinity, right? But the expected value of the first moment, of the absolute value, sorry, the absolute value, I mean, this is something that is non-negative, and it will be infinity plus infinity is infinity. I mean, we can say this. Infinity plus infinity is infinity, but infinity minus infinity, question mark, okay? So this will be the case in which we say that the moment does not exist. So basically, the first moment of a random variable does not exist if you go and compute expectation of x plus and expectation of x minus, and each one of them is plus infinity. So in that case, the random variable does not have a first moment. The first moment does not exist. It is minus in no, because each one of those guys is non-negative. So the expected value of x plus is a finite positive number, and the expected value of x minus is plus infinity. But what is x in terms of those guys? X is x plus minus x minus. Right? To restore the negative part of x, yes, exactly. We have subtraction here. To restore, I mean, x plus and x minus each are non-negative, but to restore x is a general random variable which with positive and negative values. So you need a minus sign here. Basically, you can again verify that basically this is what you will get.
Yeah, I understood that, but in the definition you said that the expectation is from 0 to infinity, like the range.
Yeah, for non-negative random variables. For non-negative random values. So this is x. This is this one here. X is non-negative. So this is basically for non-negative. Okay, this is for non-negative random values. So it always exists for a non-negative. Why it always exists for a non-negative random variable? So now, given this table of the 4 cases, it always exists for a non-negative random variable. So let's revisit this. Now, for a non-negative random variable, x plus is equal to x, right? In this particular case, and x minus is always equal to 0, right? Because x is actually is always non-negative. So what is the minimum of something that is non-negative and 0? It is 0. And what is minus 0? It is 0. So for basically for a non-negative random variable, if you define for it x plus, it will be x. X minus will be 0. And the expectation of, so basically that's a random variable that is equal to 0 almost surely with probability 1. And so what is its first moment? So the first, yes, for the general random variable, the expectation can go from it. So for a general random variable, it can be, okay, so let's write it there. So for x general, now the expected value of x can be from minus infinity to infinity, or, so now we have this possibility, okay, it doesn't exist. Okay, so good question. So now we can like put things in perspective. So for a non-negative random variable, the first moment is something that is a non-negative real number or plus infinity. It always exists, no problem. Again, because basically you are never in the situation of expected value of x plus and x minus simultaneously being equal to plus infinity, because expectation x minus here is. Now for a general random variable, if you compute the first moment, you may get anything from that is a real number, including negative values. You can get minus infinity, you can get plus infinity, or you may be in a situation in which you are dealing with a random variable without a first moment, for which the first moment does not exist or is undefined. Okay, so this is basically the story of the first moment, and you can basically extend it like as we will see. So suppose that we have our no, it doesn't exist. You cannot define it in following the mathematical rules that you basically use in defining what a first moment is. Again, because if you do this, I mean, what is infinity minus infinity? What is infinity minus infinity? Now, what you can do, I mean, like, okay, so let's it may be like a digression, but what we are doing here is very close to actually improper integrals. Like if you have a function, let's say function of alpha, g of alpha, okay, and you see something like this. You see something like this. How do you understand it? So if you find an integration over R, so from minus infinity to infinity of some function, g of alpha d alpha. Alpha is again some abstract variable. Now the correct way actually of doing this, okay, is basically to split this into two parts, okay, and basically do this. So we take limit d goes to minus infinity of d to 0, g of alpha d alpha, plus limit c goes to plus infinity 0 to c g of alpha d alpha. Okay, so basically this thing here again, if you go and read about integrals initially are basically defined only for some like interval from a to b. You know, those are called improper integrals. We write them like this, but actually they mean something more complicated. Okay, you need actually to do limits, and in the case of going from minus infinity to infinity, you need to split. And actually, there is a proof that if your function is integrable, basically your result will not depend on the split. So it is customary to basically split at 0. So you need like to integrate from some negative number to 0, and then take the limit as this negative number becomes minus infinity, tends to minus infinity, and the same here. And you say that this integral exists if, you know, basically, you know, again, you'll have issues now. What if those limits do not exist? Or what if one of the limits is infinity and the other is minus infinity? Okay, so basically in integration, this is actually the meaning of integration, right? Now you may, you know, what about something like this? Limit L goes to infinity minus L to LG of alpha d alpha. So note that this is a different animal. Basically here we are making the upper and lower limits of integration there. Basically one of them is the negative of one another. So this thing here is, but this is a way of extending integration. So this may not exist, and so people, if you are desperate in finding some integral for some application, you may actually define integration from minus infinity to infinity this way. This is called the Cauchy principal value. Okay, so now this thing may exist, but this other thing may not, you know, it may not exist. Okay, so for example, if you integrate, what is the integral of minus infinity to infinity of, let's say, x dx? What is this thing? Now if you apply the rule that basically it is the integral, you know, minus d to 0 x dx, and then you take the limit, or I put it d here, d, so d to minus infinity, and this is d, plus it will not exist, doesn't exist. But actually if you integrate from minus L to L x dx, and then you take the limit as L goes to infinity, this integral is always equal to 0, and so this will be 0. So I mean, things depend on how you mathematically define them. Okay, and so and again, like, things are tricky when you have like those infinities and so on. And so the basic definitions of a first moment will disallow, you know, the existence of a first moment if you basically, if you are in a situation in which the expectation of x plus and x minus both are equal to infinity. Now, can you define something for those? Well, I mean, you can do, and you can assign a meaning if needed, right? Again, it's also us who assign meanings. Okay, so these things are not like, they are not written on the book of the universe or something like that, right? Everything here is like, you can think of it as like a human construction. Okay, so this is our basically PMF. So we have the x is equal to small x with this probability. Okay, and so what is basically what is the expectation of x plus? So here x can be any integer excluding 0. So so again, x here, let me write it like sort of explicitly. X here is it can be equal to every integer but not 0, 2, 3, all the way. And it is equal to the probability that big X is equal to small x is 1 over 2 zeta 2. Again, this is like from the previous lecture, this is a normalization so that the sum of the probabilities is exactly equal to 1 over x squared. Now, what is x plus? So x plus will be basically when x takes the positive values. So in terms of a summation, it will be the summation x from 1 to infinity of x over 1 over x squared. So I took this normalizing constant outside, and this is the harmonic series, so it explodes. Now, what about x minus? You will now sum over the negative guys, so this is from minus infinity to minus 1. Again, this is also infinity. You can just do a substitution, y is equal to minus x, and you will also get the harmonic series, the sum 1 plus 1 over 2 plus 1 over 3 and so on. This is also plus infinity. So this is an example of a discrete random variable for which there is no first moment. Cauchy random variables for basically for a continuous case. So again, those are and you know we'll use them later. Later they are very interesting. They don't have again. This is a continuous. The Cauchy random variable is an absolutely continuous random variable for which there is no first moment. Okay. We are excluding 0 because this is how the random variable is defined. It does not take 0 as a value. So we are not excluding 0. We are not excluding 0 here, like by definition. But then there is something else. Like when you compute the expectation, like what do? You for a discrete random variable. For a discrete random variable, you take the value and multiply it by its respective probability, right? So assume that even you have a discrete random variable that, for example, takes the value 0 with probability 1/2. But when you compute the moment, this term will disappear because you will take 0, right? So suppose, let's say the Bernoulli random variable, so Bernoulli B. Okay, what will be the, so this is a random variable that is 0 with probability 1 minus p, and that is 1 with probability p. So what is the expected value of x? So again, the idea is, the conceptual idea is you take each possible value and weight it by its probability. So you take 0 multiplied by 1 minus p plus 1 multiplied by p. But this will cancel anyways, and so you are left with p. Okay, so even if you have a discrete random variable that can take a value 0 with a strictly positive probability, when you compute the first moment, basically the respective term will just disappear because you are taking 0 multiplying, regardless of its probability, then this term will be 0. Okay, but here in our example, if we go back to this example, actually the probability that big X is equal to 0 is 0. I mean, by definition, this is how the random variable, it is excluding 0 from the possible values of big X. Okay, now the formulas that you may know from previous life regarding the first moment, so note, for example, in the absolutely continuous random variable case, now you have your integration from minus infinity to infinity. Okay, so those are basically useful, and you can just use them once you make sure that basically you are in the situation where your random variable has a finite first moment. So if the first moment is finite, which automatically means that the absolute first moment is also finite. So remember, basically expected x is finite if and only if expected. So they are both finite together. Is finite. Then in that case, you so if you want to find the expected value of a Gaussian random variable, which basically extends from minus infinity to infinity, then basically for Gaussian, fx of x, it has this form 1 over square root 2 pi sigma. The standard, this is the standard form of a Gaussian distribution over 2 sigma squared. And if you want to compute the expected value, take expected value of x, then you basically do this guy. It's always finite for Gaussian random variables, and you take x, you multiply by this PDF, okay, and you do the integration. And in our case here, if you do the integration, basically you get this parameter here, which is mu. Okay, but now you can do the integration from minus infinity to infinity. So for non-negative random variables, you do the integration from 0 to infinity. For general random variables, you go for this business of integrating from minus infinity to infinity, but you need like to somehow make sure that the first moment is finite. Okay. Okay. In practice, we typically and I like alluded to this like earlier in the lecture that sometimes actually it is like more interesting to deal with certain functions of random variables. So if you have random variable x, you are more interested like in g of x, where g of x can be like x squared, exponential of x, logarithm of x, if you can define something like this, and so on and so forth. So in many practical applications, we are actually interested in functions of random variables. Okay. So again, those functions, there is this sort of fundamental question: are they themselves random variables? So let's agree among ourselves that in this course, any function applied to a random variable will yield a new random variable. You do not need to. Here, I am saying that the function should be Borel measurable, but you can simply, take it for granted that g of x, let's say called y, is a random variable. Okay. No checks needed. Okay. So how do we obtain the first moment of y? This one. Now there is the hard way. The hard way is to say, okay, so what is y? Y is a new random variable that is constructed from x. Y itself, you may obtain its distribution. You may, if x is discrete, y generally will be discrete, and you may go and obtain the PMF of y, and then use the formula for the first moment to compute the first moment of y. So the hard way is that you go and find the distribution of y, and then use the formulas to obtain the first moment of y. It turns out you do not need to do so, because actually obtaining the distribution of y may not be an easy task. We will talk about it because sometimes you really need the distribution of y in your application, but if you are just interested in computing the first moment of y, you do not really need the distribution of y. You can still work with the distribution of x. And so here is basically a very nice result. It tells you that the expectation of g of x, so this is a function of x that gives you a new random variable, let's say y. Now, if x is discrete, the function applied to the discrete random variable will give you a new discrete random variable. And again, we'll take this for granted. What you do to obtain the first moment is that you take so you apply g to all possible values of x. By doing so, you are basically getting all possible values of g of x, the new random variable. And then you multiply each one by the probability of x, right? So this thing here is summation k, g of xk multiplied by the probability that big X is equal to xk. And you do the same for continuous in the continuous case, but rather than using the PMF, you use the PDF. So again, this is, sometimes people forget about this thing, and when you have a transformation of random variables going from applying a function to a random variable to obtaining a new random variable, you start basically obtaining the distribution of this new guy, and if it's not needed, again, you are wasting so much time. Like, again, finding the distribution of y may not be that straightforward. So if your interest is just in the expectation of g of x, you can basically apply the formulas of the first moment. It is just that rather than using x, you replace it by g of x, and that's it. And you use the distribution of x itself. You do not need like to go and obtain the distribution of y or anything like this. Okay, so I think this rule here, it has a name. I think it's called Lotus. So it's called the law of the unconscious statistician. And I think it's called like this, the law of the unconscious statistician, because like people think that this result is like sort of like intuitive, but of course, you know, nothing is really intuitive, and you know, it has a rigorous proof based on like measure theoretic arguments. Okay, I will do a proof here, a simple proof here for the discrete case, but you can prove it that it's generally using these formulas will give you the correct results. Okay, and again, Lotus is your friend. It is very important to realize that if you are interested in an expectation of a function of a random variable, you know, do not go for the distributions unless it is needed in some, you know, in some other part of your, you know, problem or your whatever you are doing. Okay, so why is this true? Let's do it for the discrete case. Y is g of x. We are interested in the expected value of y. Now, basically, by definition, this is the expected value of y, and it needs the distribution of y. You need to basically say, okay, what are the possible values of y? And for each value, you take each value and you weight it by its respective probability. And then you sum, and this is by definition the first moment of y. But again, the story here is that we want to avoid this thing. We just want to use the distribution of x that we have. Here is the story. What is the probability that big Y is equal to small y? So, you know, so x, it takes values, and y, these are the values of y, and there is a mapping, you're right? So y is g of x, you take, you know, values from x and assign them to a certain y value, so this and this to this, and this. So you do a map from x to y. Now you ask yourself, what is the probability that big Y is equal to some small y? So this probability is a summation over small x such that g of small x is equal to small y. Again, what is the probability that big Y is equal to this small y? You simply go all possible values of x that are mapped to this small y, and you sum the probabilities. This will give you the probability that big Y is equal to small y. Okay, so this is basically, this thing here is the probability that big Y is equal to small y. You go to basically, you sum the probabilities of big X at the values that are mapped by the function g to this particular small y. Second step in the derivation is basically to rewrite this summation, okay, to take this summation here and rewrite it over all x. Okay, so basically the summation should be on the values of big X, the small x's that are mapped to small y. Now, if you replace this by a summation over all possible values of big X, you need to basically introduce this indicator function so that if there is a small x that is not mapped to small y, this indicator function will be a 0, and if the small x you are talking about is mapped to small y, then this indicator function is equal to 1. Okay, so this is a rewriting of the first step, again relaxing the summation index small x to include all possible values of big X. But to have an equality here that makes sense, we will need to introduce an indicator that is equal to 1 if g of small x is equal to small y, and that is equal to 0 if g of small x is basically something else, something that is different from small y. Okay. Now, what if we can interchange? Okay, so here you need like to do the summation with respect to small x, and then after finishing that you do the summation over small y. Let's suppose that we can interchange. Now, are we justified forever in doing this interchange? Of course, no. But there are cases in which this interchange is perfectly okay. For example, if basically the possible values of big Y are all non-negative, then everything here will be non-negative. So Y will be non-negative, the indicator function is 0, 1, and the probabilities are non-negative. And so by Tonelli's theorem, Tonelli tells you if you have a double sum of a real valued quantity that is non-negative, you can do the summation in any order. You can do the double sum in any order of your choice. Okay, so there are basically theorems that can be used to justify basically the interchange of the two sums. So if one of those theorems works and you can do the interchange, then you can basically do the summation first with respect to y, and then later with respect to x. So we have this summation. What is this summation? It is the summation over the possible values of y of a small y, that is here, from the definition of the first moment, and then you have this indicator function that was introduced when basically we extended the summation with respect to small x to include every possible value of big X. So think about this summation. When we implement this summation fixing small x, what will happen? What will happen? Okay, so basically what you are doing here is that you are sweeping through the values of y. For every possible value of y, basically g of x is some value. So let's suppose, let me write it. Suppose that g of given some x, g of this x is equal to y tilde. This small x is mapped to y tilde. Then what happens when you sweep through the values of y in the relation? If y is different from y tilde, so if y not equal to y tilde, this is 0. Indicator is 1 only when y is equal to y tilde, which is g of x. So basically this summation here, the only surviving term will be when y is equal to the value g of small x for each particular value of small x. Note that when we do this summation, we fix small x because it is the outer sum. So basically this summation will give you y tilde, which is g of x. And what is this thing? This is the formula that we have here. It's basically that you sum the values of g of x. Do you need the distribution of y? No, using this formula, you can just work directly by the distribution of x. Okay, so locus, again, so important. If you want the expectation of a function of a random variable, you do not need to find the distribution of the new random variable big Y, which is g of x. You can just apply, this formula in the discrete case, this formula in the continuous case. Okay. Now, and of course, you see that, is this all, can you find a counter example in which this will not work? Yes, because the proof relies in interchanging the order, and interchanging the order, may not basically be valid under some situations. But for our purposes in this course, go for it. Basically using Lotus will, I don't recall any case in which this will be invalid. We need to interchange the order because we want, so the rationale of the proof is that rather than having a summation over y, okay, and the distribution of y, what we want to do is to have a summation over x, right? And so it is to start with the definition of the first moment, which will be a summation over y, and it will require the distribution of y. We should know those probabilities, but then you express those probabilities in terms of the x probabilities, okay? And then if you want everything to be in terms of x, then you need basically x to be the outer summation. Okay, so the interchange was done so that we have a summation over x that basically involves also the probability that big X is equal to small x, and you don't really need to compute this thing. So basically, this probability is not needed. In the formula, if you see it, is not needed. Because this probability can be like tricky, and sometimes it's needed, by the way, on its own. So sometimes actually you will be asking, find basically the PMF of Y. Okay, so in that case you have no other option but to go and find the PMF of Y. But if your business is just the mean, the expectation, then you can just go for here. The interchange again was done so that we do things with respect to the old, you can say the old random variable big X, rather than basically computing the distribution of the new random variable which is big Y. So this interchange is needed, but how to justify it? There are, for our purposes, it will be justified. Now the expectation, it has like properties that we need like to keep in mind. If X is equal to C almost surely, okay, then expected X is equal to C, because like X is equal to C with probability 1. So what is the expected value of X? It is equal, how do we compute the first moment? The possible values of the random variable. Here it only takes the value C with probability 1, and so C times 1 is C, and that's it. Okay? Now, what if we have an indicator function? Okay, what if g of x is indicator x is in some interval or something like this? For those random variables that are like an indicator functions, basically the first moment is always the probability that the indicator function is equal to 1. Why is this the case? So if g of x is equal to the indicator of some condition, like here x is in some b, some set b, then this is equal to 1 or 0, right? It's equal to 1 or 0. So basically indicator x is in b, it is 1 with probability that x is indeed in this set b, or 0 if x is not in b, because in that case the indicator, the condition inside the indicator will be violated and the indicator will be 0. Now 0 times anything will be 0, and so you are left with the probability that x is in b. Okay, and again, if x is Bernoulli b, so this is something very similar. So x equals 1 with probability p, 0 with probability 1 minus p. What is the expected value of x? Same story I said before, that it will be 1 times p plus 0 times 1 minus p. You take the possible values, you weight them by the respective probabilities, and this will be p, which is the probability that x is equal to 1. So for those random variables that are 0, 1, okay, basically the first moment is the probability that the random variable is equal to 1. So this is general and useful, like to keep in mind. If your random variable is a 0, 1 random variable, it's 0, with some probability, it's 1 with some other probability, then the first moment, the expectation, the mean of this random variable is simply the probability that this random variable is equal to 1. Expectation is linear, okay, and so basically the expected value of something like this, where those are basically constants, is you take the expected value of x1, you multiply by c1, expected value of x2, multiply by c2, and then you add. So it is a linear operator. It is linear. Now, if one random variable is less than the other random variable almost surely with probability 1, then you apply the expectation and the inequality will be preserved. Okay, so this is very useful and we will use it later. So almost surely apply expectation to both sides. Okay, we will need this in various applications. It is true that this one is less than or equal to this one. Okay, so this is again another property and you again, it's all these things can be if you define expectation like using measure theory and so on, all of these can be derived rigorously. Then we have one important inequality. It's your friend. It's the triangle inequality, which it's the triangle inequality, which tells you that if you compute the expected value of a random variable, okay, and take the absolute value, this is always less than or equal to the expectation of the absolute value. Okay, so let's again see. It's because when you say that a random variable is less than another random variable, are you talking that this happens with probability 1, or it is not always with probability 1? So yes, very important. Right? In this course, by the way, later we will basically compute things like this. What is the probability that some random variable x2 is greater than some random variable x1? If this probability is not exactly equal to 1, then this is not applicable. Okay, so good question. So basically, yes, if x1 is less than or x2, almost surely, which means with probability 1, then the expected value of x1 is less than or equal to the expected value of x2. If the probability that x1 is less than x2 is something like 0.7, then this rule may not hold. Okay, so almost surely here is very important. Okay, so those are things keep in mind. I mean, they should be like part of of your thinking when you solve any problem. Right, so the first moment of a random variable x that is constant almost surely is the constant itself. If your random variable is like a Bernoulli random variable that it's 0, 1, it takes the value 0 or 1, then the first moment is the probability that the random variable is equal to 1. Expectation is linear, so the expectation of a sum of random variables will simply that you compute the expectation of each guy and then you sum them. Okay, now if x1 is less than or x2 almost surely with probability 1, then you can apply expectation to both sides of the inequality and the inequality will be true. And then you have the triangle inequality, which is that the absolute value of the expected value of x is always less than or equal to the expected value of the absolute value of x. Okay, so those are very important to keep in mind. We can define the pth moment. Okay, so we talked about the first moment. So the pth moment will be that you compute the expectation of expectation x to the power p. Okay, and if the power is an even number, then basically this thing always exists, right? So for example, expectation x squared, right? X squared is always non-negative, right? So this always exists in 0 or infinity plus infinity included, right? And generally speaking, if this guy here is an even integer, then again raising if you take a general random variable that can be positive or negative, but if you raise it to the power an even power, then it is converted to a basically a non-negative random variable, and so now you can always find those even order moments of a random variable, and of course there is a possibility that the expectation of something like x squared or x to the 4 will be plus infinity. Okay, so what is the formula? Okay, so if expectation x of b is finite, okay, then expectation x of b, let's say that it is continuous case. Let me write the continuous case. You will integrate from minus infinity to infinity, small x to the power p, then the pdf, and then dx, like this. You do not need, this was basically the story of the previous slide, you do not need like to call this thing y and go and obtain the distribution of y and then use its PDF if it has a PDF. No. Lotus, law of the unconscious statistician. Think of x to the p as a function of x. And how do we obtain the first moment? Apply the function to small x, multiply by the PDF of x itself. Integrate, and you are fine. Sometimes we define central moments. So the central moments, we subtract the mean before we raise to the power p. Okay? And of course, this presumes, under the assumption, that expected x is finite. Okay, so for random variables for which the first moment is finite, you can define something called the central moment, and the central moment is like the first moment, but you subtract this x, which will be a number, which will be a finite number, before basically computing the expectation. So the b central moment will be not the expectation of x to the power p, it will be x minus this number, the expected value of x, all raised to the power p. And of course, for this for this subtraction to make sense, you will need expected value of x to be defined, and you need it to be a finite real number. Okay. And the absolute moments, you apply the absolute value first, and because you apply the absolute value, you basically convert the random variable into something that is always non-negative, because the absolute value is always non-negative. And so the absolute moments always exist as finite real numbers or as plus infinity. Okay. And when we talk about the absolute moments, actually we can make this p here not. So can you do something like this? 1.75. Yes, you can do. Okay, so you can basically do these moments. Not used. Typically, we are interested in integer values of p, and those have meanings. So as we will see. But like mathematically speaking, you can like do something like this, and it is okay. You can compute it. If it means something to you in some application. Now, how are the absolute moments related to one another? So this is like sort of an important thing that will like clarify for us like theorems that we will see later in the course. So suppose that you have q and b, and q is greater than or equal to b greater than or equal to 1. So what is this thing? Versus this thing. In other words, if you have a random variable, and then you are interested in the qth absolute moment and the bth absolute moment, and you know that q is greater than or equal to b. Now, are these guys like somehow related? Like, for example, that one of them is always greater than the other for all random variables? Okay, or is it basically the case that one of them is always greater? So we want like a relation. So basically, one way of solving this relation is something called the Lyapunov inequality. But this we will study later. So we will later basically link these two guys by something called the Lyapunov inequality. But for now, I will basically talk about like I will do things like in a different way. Okay, and so let's see. How can we relate these two guys? So this is expectation. This is expectation absolute x to the power absolute x to the power p, right? So now you will see tricks that are very, very useful in probability. So this guy here is like multiplied by 1. It's multiplied by 1. So you can write 1 as the indicator, right? That absolute x is less than 1 plus the indicator that absolute x is greater than or equal to 1, right? The absolute value is either strictly less than 1 or it is greater than or equal to 1. One of those indicators will be 1 and the other will be 0. Right? So basically, if the absolute value of x is less than 1, this indicator will be 1. So we can 1 and 0 if x is less than 1. And if x is greater than or equal to 1, this will be 1 and the other will be 0. So in both cases, I can write 1 as the sum of these two indicators. Again, you may see that this is like a trivial thing to do. It's extremely important, and use it like in many derivations in probability and statistics. So expected value of x to the power p, take the 1 and write it as the sum of two indicators, basically that are 1 exclusively. So if one of them is 1, the other is equal to 0. And so the conditions here must basically sort of partition the space of possibilities. So absolute value of x is either less than 1 or greater than or equal to 1. And so that's it. I mean, there are no other options. And so we can write this one here as the sum of these two indicators. Now, expectation, we will take it for granted that expectation is linear. So if it's linear, then we can split this expectation of a sum into two expectations, and then we can work with each one on its own. So thanks to the linearity of expectation, I can do this splitting here. And the linearity of expectation is something like the linearity of integrals. Okay, it is not far from the idea of linearity of integrals. The integral of the sum of two functions, you can integrate the first and the second and then sum. It's the same story here. Okay. Now, this is basically the first expectation that we need to compute. Okay. So here is the claim. The claim is that this xp indicator x less than 1, so this thing is less than or equal to indicator absolute x less than 1 almost surely. Why is this the case? So I am saying that this thing that we are taking the expectation of is less than or equal to just the indicator almost surely, which means that this is guaranteed, right? It's with probability 1. Why is this the case? So if you want to like verify inequalities as such, just sweep through the possibilities of the indicator function, right? So basically, if absolute x is greater than or equal to 1, then this left-hand side is 0 because the indicator is 0. Right-hand side is 0, and we have 0 is less than or equal to 0. That's a valid mathematical statement. Okay? So it's true. Now, what if the absolute of x is now strictly less than 1? Then the indicators are both equal to 1, and so we have xp, x to the power p, is less than or equal to the indicator, which is 1, which is also true because the absolute value of x is less than 1. And so the absolute value of x raised to the power p will also be less than or equal to 1. If you take a fraction, something that is less than 1, you raise it to any power, then basically you get something that is also less than or equal to 1. So this is always true. And if it is always true, then what did we learn? So remember that if we have basically z less than or equal to y almost surely, then expected value of z is less than or equal to expected value of y. Okay, so this is basically what we will do here. That we are interested in this expected value. Now, we know that basically whatever is inside this, it's always less than or equal to the indicator alone. It's as if we are replacing this guy by 1. So this expectation here is less than or equal to the expected value of the indicator. Now, what is the indicator? It is something that is 0 or 1. So in the previous slide, we said that the expectation of something that is either 0 or 1 is exactly equal to the probability that the indicator is 1. And the indicator is 1 if the absolute value of x is strictly less than 1. And any probability in the universe is less than or equal to 1. So basically the first term is upper bounded by 1. Now let's go to the second term. So for the second term, here is what we have. We have the expected value of x raised to the power p, and now we have the absolute value of x is greater than or equal to 1. Okay, so if you have a number that is greater than or equal to 1 and you raise it to a higher power, okay, so you have x, absolute x. Now it is greater than or equal to 1. So what is absolute x to the power p versus absolute x to the power q if we know that q is greater than or equal to p? So if you have a number and this number is greater than or equal to 1, raising it to a higher power means that basically this is less than or equal to that. Now this is not true. Like if you have 1/2, squared is 1/4, but if you raise it to the power 3, it will become 1/8, which is smaller. So basically this is true again if your number is greater than or equal to 1. And so basically this is the idea why we did the split. We did the split so that we have these two cases. To replace p by q, we will need the absolute value of x to be greater than 1, so that we say that if we take, basically the absolute value of x raised to the power p, it will be less than or equal to the absolute value of x raised to the power q. But this requires that this is true here. Okay? So, and the absolute value of q multiplied by the indicator that x is less than or equal to 1, this thing here is less than or equal to absolute value of x, almost surely, right? Because the indicator function is 0 or 1. So if it's 0, then 0 is less than this guy. If it's 1, then absolute value of x raised to the power q is less than or equal to absolute value of x raised to the power q, which is a correct statement. I did an upper bounding step. I'm not saying equality. So going from here to there, so this thing here, okay, this thing, so maybe what is missing, maybe this is what's going, this is less than or equal to. This is not equality. So I'm not saying that this is equal to this. It's the power of q. But if we replace p by q, then we have this quantity is less than or equal to this quantity. Again, because we have a number that is greater than or equal to 1. So raising it to the power, to a higher power, so because q is greater than or equal to p, raising it to a higher power leads to a higher value. And then we can say that the indicator function is less than or equal to 1. And so basically this expectation is less than the expectation of x to the power q. So let's recap what we did here. I started with this guy. Okay? I started with this guy. Now, first trick, again, if you have not seen it before, it is very important in probability and statistics. Then I rewrote this thing as two terms. So indicator, because we have two possibilities, either this is less than 1 or this is greater than or equal to 1. We have two possibilities. So we started by, again, replacing this one here by the sum of two indicators, and these two indicators are chosen such that one of them is 1 and the other is 0. We have only two possibilities, either this is 1, the other is 0, or vice versa. And of course, to write the expectation as the two expectations, we exploited the fact that expectation is linear. So expectation of the sum of two things, of two random quantities, will be the sum of expectations. Now what we did is that we upper bounded each guy. So this one was upper bounded by 1. And this one was bounded by the expectation of x to the power q. Let's repeat this case here. How did I achieve that upper bound? The upper bound, I said basically, if x, okay, so let's put it like this. x to the power p indicator x absolute x greater than or equal to 1 is less than or equal to x to the power q indicator absolute x greater than or equal to 1. Almost surely with probability 1. Why is this true? Why is this true? Now, if absolute value of x is less than 1, then you basically have the inequality 0 is less than or equal to 0, which is a valid inequality. But the interesting case will be, what if the absolute value of x is greater than or equal to 1? In that case, the indicators are both equal to 1. So the claim is that the absolute value of x raised to the power p is less than or equal to the absolute value of x raised to the power q, which is true because if we take a number that is greater than or equal to 1 and raise it to a higher power, and the higher power here is q, then you get a higher quantity, a greater quantity. Okay? So, and this one here is less than or equal to, so this guy is less than or equal to the expected value of q because the indicator function is less than or equal to 1. So we upper bounded the first term by 1 and the second term by this quantity. So this is our result. Our result is that expected value absolute to the p is less than 1 plus expected value x to the power q for q greater than p. So this is an inequality. Then what? Then what? Okay, and why is this thing even useful? Okay, outside of course, curiosity that you want like to do to establish relations between the various moments with different powers, but actually this is good, like even like in applications, because suppose that, so this is case 1, suppose that this guy is finite. So suppose that you compute the absolute moment, the q's absolute moment of some random variable, and you get a finite number. What is your conclusion? What is the conclusion? If this guy is finite, a finite number plus 1 is a finite number. So is finite for every p less than or equal to q. In other words, if I tell you, so example, if expectation x to the 3 is finite, so suppose that I tell you a theorem, and in the statement of the theorem, it is mentioned that our random variables, they have a finite absolute third moment. So what is the conclusion? So what about this one? Finite. What about the second moment? Finite, guaranteed. Guaranteed. You don't need to check them or anything. Anything lower will be guaranteed to be finite. So I don't need like to go and say, suppose that our random variables, they have a finite, first moment and a finite second moment and a finite absolute third moment. No, you just need to say that the random variables, they have a finite absolute third moment, and basically it is understood that every other thing, we are talking this, it should be the absolute value. The other guys will be the idea of using the absolute value is that the expected value, if you convert a random variable and use its absolute value, the absolute value is always non-negative. So basically those expectations are well defined. Okay, so those guys, those are living in 0 to infinity. We are not in this weird situation which like this guy does this or something like that. So so that's like non-negative random variables, they have like this sort of advantage that you can always talk about their moments or their expectations in terms of finite numbers or infinity. We are never in a situation which like you say that the moment does not exist, okay, because they are always non-negative. Okay, what else can we conclude? Okay, so basically this is the second case. Suppose that suppose that this guy is plus infinity. If this guy is plus infinity, then we are guaranteed that all higher moments, all higher absolute moments will also be plus infinity. So conclusion would be that expected value Q okay. So again, those things will appear. I mean, like for example, one of the most important, you may already know it from a previous course, the central limit theorem. So in central limit theorem, you find this. Suppose that our random variables, they have a finite second moment. A finite second moment. Okay. So basically, what is the importance of something like this? So if the second moment is finite, then we are sure that the first absolute moment is finite. And if the first absolute moment is finite, then it is automatically the case that the first moment itself is finite. Actually, let me write this down. So one application again. If a theorem tells you that this is finite. Conclusions. So we have a list of conclusions. Okay, so this thing is the same as expectation of absolute x squared. Okay, is finite. Then conclusions. Is finite. Finite. First absolute moment. But also, this is finite. Finite first moment. So there are two ways of seeing this. One way is to go and revisit the table with the four cases. In the table with the four cases, you will find that basically these two guys are finite together. Or another thing is to remember the triangle inequality. The triangle inequality. So this is the triangle inequality. Is that this is always less than or equal to that. So if this guy is finite, less than infinity, then this guy must be finite. Okay, so these things should be like in your mind, because like theorems really do not tell you these all conclusions. As you will see later in the course, again, if there is a constraint on the moment, it will be mentioned something like this: we want a finite second moment. That's it. You need to make all these conclusions. So finite second moment. The second moment is the same as the second absolute moment, because squaring x squared is the same as absolute x squared. What are my conclusions? Then the first absolute moment is guaranteed to be finite, and then the first moment is guaranteed to be finite. Not only does it exist, it's also finite. Okay, so this is one thing, like sort of, rather than writing a big story about the moments of random variable, we can capture many things by using this inequality in this. Basically, we just said that basically that if this guy is finite, then for b less than or equal to q, we are sure that those are finite. And if this guy is infinite, then for q greater than or equal to b, we are sure that this is plus infinity. Okay. And again, this is not the end of the story. You will see this story told in a different way when you study the Lipinov inequality. Okay. So the variance. The variance is the second central moment. Okay, so there are several ways of understanding the variance. Okay, so one will, like the dry is variance is second central moment. So if it's the second central moment, it means what? like you take expectation not of x squared, you subtract the first moment first. Okay, so we'll assume, so assumed to be finite. Okay, and so this is basically the variance. So this is one way. So the variance of a random variable, is basically you take x minus the first moment of x, and then you square, take the expectation, and this number will be from 0 to infinity. Again, we are talking about guys for which the first moment is defined, and it is a finite number. So it is the second central. Now, there is a question. What if I tell you that the random variable has a finite second moment? Then does it have a finite central second moment? Okay, so in us that we are here like in a situation, if what is the relationship between relationship between so suppose that the first moment is finite. Okay, so how these two guys are related? So if I know that this is finite, is this other guy finite or not? So it turns out, and this is something that you will do in the tutorial session on Tuesday, is that expectation to the p is finite. So if this is finite, then in other words, these two guys are finite together or infinite together. Okay, so basically, if you have a random variable, you subtract something. So basically, what you will take in the session will be basically a very general statement. If you subtract anything, not necessarily the mean or anything, if this is finite, then this is finite, and vice versa, of course, because you can interchange the rule of A and B. So in other words, if the absolute moments are finite, the corresponding central moments will also be finite. Okay, the absolute ones will also be finite. Okay, so now for me, I mean, the variance, we need like to discuss sort of its meaning. So I think for the meaning, let's postpone this to the next lecture. Let's just do some calculations now in the last 5 minutes of the lecture, and then for the meaning itself. Without the, no, for the second moment, basically this thing, right? So if you have a number, x squared is the same as absolute x squared. Right. So let's put it generally, for moments of even order, basically the moment is like the absolute moment, because basically taking the absolute value and then raising it to an even power is the same as like just taking the random variable itself, raising it to this even power. Okay, no problem. Okay, so for the meaning of the variance, we'll try like to. The variance can be 0, the second moment can be 0, and this will be in the next lecture. Yes, it's a very important question, by the way. What does it mean if the variance is exactly equal to 0? It can be 0. So as you can see from here, it can be 0. So variance x equals 0. Yes, it can be the case, and it has a meaning. Okay, it has a meaning that it will actually derive. So we will not just say it. We will actually drive it in the next lecture. But for the remaining part of the lecture, I mean, let's like do like things like that are like automatic. You know, the variance. This is the definition of the variance. It's the second. It's the second central moment. It can be written in a different way. Okay, and so let's do it. It's another form that is useful. So this is the variance by definition. Expand the square. So if you expand the square, this will be x squared plus expectation of x squared, and then minus 2x expectation of x. Okay, so there is another form for the variance, which is this one here, that you get the variance by subtracting the square of the first moment from the second moment. And of course, it is exactly equal to the variance. So how can we get from the first formula, in which you subtract the first moment, square, and then take expectation, how it's equal to this one? So again, the derivation is just one line. You take the definition of the variance, you expand the square, and then you exploit the fact that expectation is linear. So the expectation of things that are summed together, this thing is equal to expectation x squared, right, plus this one, expectation x squared, and this one will be minus 2 expectation x squared. So this is the square of the expectation, same story here, and this will be expectation x squared minus expectation x squared, right? Because we have minus 2 here and the plus 1 here. Okay, but let me like comment on something that, you know, some students find confusing, which what exactly did I do here? So expectation x, okay, so expectation x squared, apply the expectation to it, right? So again, I expanded the square, I wrote it as 3 terms, as you have been doing like since many years ago. Then I applied expectation. So what is expectation of x squared? The expected value of x, you know, again here I am talking, once we compute the variance, we are talking about random variables for which expectation of x is a finite number. Expectation of x is a number. So this is a number that is, this is a constant. And so the expectation of x squared is expectation x squared. Again, the general rule is that expectation of c, constant, is just c. Okay, everyone can see this? Okay, again, because these things, you know, things will be complicated later when like we have a bunch of random variables, and inside our expectations there will be like x's and y's and z's and so on. Now, if there is a constant and expected value of x is a constant, if you think of the expected value of x as a random variable, then it is a degenerate or constant random variable. It is a number. So expectation applied to it will give you a number. And then finally, what is expectation of minus 2 expected value of x? Now this is a constant. This is like expectation of a constant multiplied by x. So this is constant. And expectation is linear, so you can pull the constant outside. So this is c expectation x. And so basically this is minus 2 expectation x. That's the constant expectation x. And so this is minus 2 expectation x squared, which I wrote here.